So, hello everyone. My name is Sergio Lopez and I work as a software engineer in the automotive team at Red Hat. And this talk is kind of a continuation of Dorinda Samatik's talk beforehand, but with a focus on the many personalities, many ways, many one languages that the virtio-gpu device is able to interpret and talk. I'm also going to talk about a couple of real-world use cases in which we make use of those different personalities. Now, I think most of us working in virtualization are used to relatively simple virtual devices. So you usually have your device implementation on the VMM, and then you have some kind of driver on the guest host, on the guest kernel, and basically that's basically it. Basically that's it for many devices. But virtio-gpu in particular is sitting in the other side of the spectrum. So yes, you have your device implementation on the VMM, you have your kernel driver on the host, on the guest, sorry. But then you also need to interact with, and the host, you need to interact, as you, Dorinda Mate explained, with virtual render, JFS stream, maybe rutabaga, potentially with the Mesa drivers on the host, potentially with a compositor on the host. And also in the guest side, you also need to interact with the Mesa drivers and the guest, the potentially a nested compositor, maybe a full compositor. So there are a lot of moving pieces involved in using virtio-gpu, and to make things even harder, there are completely different ways of using this device. So to differentiate between the different ways in which you can use virtio-gpu, it defines what they in the virtio-gpu terminology is called contexts. If we look at the kernel source code, we can see like there are these three contexts, but the reality looks mostly like this. This is what you can already see in the wild. Some of these contexts are kind of well known relatively. So VGL and VGL2 is probably something that most people in the room has used once or twice. It was the original motivation for virtio-gpu. It's a way of serializing OpenGL commands through the virtio device. Some of them are perhaps lesser known, especially JFS stream before the previous talk. Probably because JFS stream until very recently was very tied to Android. So unless you were doing anything with Android, you probably didn't have an experience with them. But in any case, in this talk, I'm going to focus on these three ones, in Venus, cross-domain, and DRM. And that's because over the last year or so, I've been involved in different projects that make use of those three contexts. But before jumping directly into an explanation of those contexts, I would like to stop a minute to think about how it's possible that virtio-gpu has so many different personalities, and it seems like it's growing every year. So if you look at the timeline that Dorinda Mate saw before, originally it was just VGL, and suddenly over the last years you get like JFS stream, cross-domain, various Venus contexts. So how is that possible? And I like to focus on three features. This being at the virtio device, you have a couple of queues. Yeah, on those queues, one is the cursor queue, while the other is the command queue. I'm not going to go deep into that because we already have the previous talk. But if we focus on the command queue, we see that there are many of them, but I would like to focus on one particular command, which is exec buffer. Exec buffer is an IOCTL and also a GPU command, which basically allows the guest to send an opaque chunk of data from the guest to the host. So in practice, what this gives you is a unidirectional opaque transport from the guest to the host. Another feature I'd like to highlight is if a f-resource blob combined with a host visible. So basically, this allows you to register a blob on the host and map it somewhere in the memory, in a memory region that will be shared between the guest and the host. So that way, both the guest and the host can share data between them in a seamless way without having to copy it around. And What this gives us is the ability to implement rings, queues, to map file descriptors. And as a side effect, it also means that the exec buffer becomes a bidirectional opaque transport because, yes, the guest can send opaque chunks of data to the host, but that now the host can reply using shared memory. So now exec buffer becomes a two-way bidirectional transport. And the third feature that I'd like to highlight is fences. Fences are mostly built on top of the conventional virtqueue communication mechanism. And what basically allows you to do is to have pullable objects. So by combining these three features, you can basically implement whatever kind of protocol you want to do on top of that. I mean, if you need a pipe, just use exec buffer. It's already a bidirectional opaque transport. If you need to pull on the pipe, you can do a fence, and then you can pull on the file on that pipe that is modeled on top of virtio-gpu. Do you need to share a file descriptor, register it as a blob, and put it on shared memory, and then you can share between both devices, both contexts. So in the end, I don't know if it is one on purpose or not, because I haven't followed the GPU history, development history so closely. But by having these three primitives, you can basically lay on top of that arbitrary protocols. So it kind of has become this kind of omni device. It's a arbitrary device. You can put anything on top of that. Okay. Having said that, let's jump directly into the contexts themselves. So the first one I like to talk about is Venus. So Venus is basically a transport for serializing Vulkan commands, Vulkan instructions. Now, I'm not an expert on OpenGL nor Vulkan, but I have been told that Vulkan is more friendly towards serialization than OpenGL, basically because it operates at a lower abstract level, so the semantics are clearer and simpler and easier to serialize and marshal. Of course, it makes heavy use of resource blobs, so there is a significant amount of shared memory between the guest and the host. Basically, every VO is going to be a resource blob shared between both contexts. And the main use cases for this is, of course, Project Borealis, which is the main motivation. This is a project from Google for bringing games to Chromebooks. So on Chromebooks, there is this Linux context, which is actually a VM. And this is in this VM is where they run games. So of course, they needed a way to expose GPU acceleration to the VM. And they developed Venus for this particular purpose. Another use case, which is one of the first real-world examples I want to give about the power of these contexts of virtio-gpu, is Podman Desktop and the need to enable macOS to run GPU-accelerated containers. So long story short, some months ago, we came up with the necessity of basically doing large language model inference using running containers on macOS. But of course, containers on macOS are Linux containers, and since there are Linux containers, they need to run in a VM. So we needed a way to expose some form of GPU acceleration to that particular VM. And the problem in macOS is that the hypervisor framework and the virtualization framework has support for GPU acceleration, but only for macOS guests. It's not exposed to Linux guests. And even if it were, there are no open source drivers, and there is no open source user space drivers either for managing that GPU acceleration device. So we needed to come with something, and we came up with this. So basically, what we do here is we have a Linux VM guest, we have a virtio-gpu device, and this virtio-gpu device is able to talk the Venus context. So then we have applications that may be using OpenCL or maybe using Vulkan as a backend. For instance, Llama CPP has not one but two Vulkan backends. They have one is called Vulkan and the other that is called Compute with a K. And those will be compiling the shaders for the workload using through Mesa into SPV. These SPV shaders will be sent using Venus for coordination to MoltenBK. And MultiBK translates these SPV shaders into metal shader languages. Eventually, those metal shaded languages are again compiled again by the metal framework in whatever language the GPU consumes. And even though this may seem like a very long pipeline, on a first thought, you may think that it's quite inefficient. In practice, compiling the shaders is something that happens just once at the start of the workload. And everything else that happens afterwards goes through shared buffers, through those resource blobs, those shared memory regions we talked about before. So in practice, once you have set up the context of the large language model, everything that is going to happen through shared memory that is visible both to the guest and the host. And in this case, it's also memory that comes directly from the GPU. It's actually device memory that is first mapped into the hypervisor, into the VMM, which is in this case is libkram, and is then injected into the application using the hypervisor framework API. So what this means is that in practice, the performance of this environment is practically the same you get in the native context. It's almost indistinguishable. Okay, moving on to another context, I would like to talk a little bit about cross-domain. So most people, or most of us, using virtualization and using any kind of display output are used to work with frame buffer. So if you run QEMU by hand and you run any VM, you will get this window, maybe GTK window is the old window that has a frame buffer. You get to see how the guest is booting. Eventually, you get to see probably some kind of compositor. But the thing is that drawing in the frame buffer is not always the best approach. On one hand, it's possibly not the best UI if you are not interested in running a full operating system. If you want your VM for running just one application, or for, in this case, for running one game, having to do that through with a full frame buffer is not the best approach. And also, the performance is potentially worse. Because the best scenario, if you want to draw in a host window, is to actually grab to draw directly in a surface of that host compositor. And that's something that can be done. You can export using DMA buff that surface from the host compositor and pass it through to the guest and have the guest draw directly into that. But to be able to do that, you need to somehow coordinate the host compositor with the guest compositor. And for that, we need also a way for both compositors to communicate. And here is where cross-domain enters the game. And this one is one of those things that kind of reinforce my argument that this virtio device has become like the omni device that's able to implement any protocol. Because in this case, it's basically a way to implement a Wayland over virtio-gpu, basically. So you can have an nested Wayland compositor on the guest, such as Sommelier, communicating with the host compositor on the host, and then run applications on the guest that appear like regular windows on the host. So it gives you better performance, as I said before, and it's also potentially the best UI. Lastly, I want to talk a little bit about DRM native context, which is quite a newcomer into the virtio-gpu world, and it's quite an interesting one. So we know there are contexts that serialize OpenGL calls. In fact, there are two, virtgl and GFX stream in the GL variant. There are also contexts that serialize Vulkan commands. And in this case, with DRM native context, we go even lower. So with DRM native context, we are serializing directly the IOCTLs directly. And now the problem of this approach is that, of course, the IOCTLs vary from one GPU driver to the other, so they are not the same. Which means that you need to have, on one hand, you need to have a Mesa driver that is aware that it can serialize the IOCTLs and push them through virtio-gpu instead of opening the actual GPU device it expects to be opening. But on the other side, on the host side, you also need a virtual renderer that is able to unpack those IOCTLs that is receiving serialized and execute it on the host side. So far, we have two implementations that are already upstream. The first one, which was developed by Rob Clark from Google, who was the one who invented this mechanism. which is the MSM or Freedreno driver. But recently we have got a new one, which is the one for AMD GPUs. And there are also two work in progress drivers, one for Intel devices and another one for Asahi, which is the one I personally contributed lately. The use cases for DRM native contests are, again, in theory, Project Borealis, but I mean, in theory, there could be Chromebooks out there using that are based on Qualcomm boards that they have a Freedreno drivers and that using DRM native contests to have better performance than Venus. But I have not formal confirmation that this is something that is actually done on the wild. In theory, it was for that, but I don't know if it's being used or not. And another real-world use case, which I've been involved with, is running commercial games on Asahi Linux. So the thing with the problem with commercial games and Asahi Linux is that, of course, Asahi Linux is targeting Apple Silicon devices, so it's ARM64, and most commercial games only provide x86 binaries. So this means that we need at least a fast user space x86 emulator, because otherwise it will be impossible to run them. A second problem is that Asahi Linux is a 16K page distribution, mainly because most devices in the hardware expect it to be like that, and the Linux kernel doesn't really support having dual pages. It's true that, for instance, Darwin on macOS is able to do that. It may have processes that are 4K or that operate at 4K granularity, and processes that operate at a 16K granularity. But this is at least not the case for Linux for now. So we needed to run a way to run a 4K kernel on Asahi Linux without replacing the host kernel. And of course, the obvious option is to run it in a VM. Now, this generated a second problem, which is VMs doesn't have direct access to graphics, and using VFIO is not an option because this is an embedded GPU on a board, so you cannot delegate it to a VM. So we needed to use something, and in this case, the solution was using virtio-gpu with DRM native context for better performance. Now, I'm trying to go and do a live demo of this, of using DRM native context with KRAM, FixEmu, and on this laptop. It's going to be live demo with one hand, so please bear with me. Okay, so this is Asahi Linux. We are running a regular kernel from the Asahi Remis, a 16K kernel. And what I'm going to do is I'm going to start a VM using KRAM. KRAM is just yet another utility that has spawned up using libkram, has VMM, that's designed specifically for this particular purpose. So it uses the root file system, has the same file system for the guest, and it also starts up Sommelier and other needed tools to actually start using running games and using DRM native context. So I'm going to start it up. Here is it. Okay, this is a freshly started VM, which is running a different kernel than this one. It does have a DRM device, and we can see, if you remember from the previous talk, we can see that we have support for VGL, resource blob, host visible, context init, all the features we need. And of course, we have access to the /dev/DRI device. So let's run some benchmarks, shall we? So this is the terrain benchmark of GLMark with a 3-second duration. It's really quick, but this benchmark is quite stable, so 3 seconds will be fine just for its illustration purposes. This is running inside the VM, and it's using DRM native context, and we get a score of 290. Now, let's run the same benchmark, bare metal. And again, 3 seconds, and we get 304. So, I mean, on the VM, we are getting like 90, 95% of native performance, so it's fairly good. But of course, running benchmark is fine, but let's run some games too, which is the actual purpose of this. So this is a game, an indie game that is called A Short Hike. It's a cozy indie game that is only available for A60C. So we are running it using a crash, of course, because it's live. This is what you get if you do live demos. Okay, now it's getting there. It's the first time it crashed for the 100 times I run it during this week. It needs to be this one. So this is a 3D game built using Unity, and it has a number of post-filtering operations to look like retro, but it's actually a 3D game. And as we can see, we are getting a fairly decent amount of FPS, like over 160. So it's perfectly playable. I mean, there are no graphic artifacts. It's working perfectly fine. We can go with something more expensive. Crossing my fingers. This is another indie game. It's more expensive in CPU terms because it's drawing a more complex world. It looks small because I wasn't sure about the size ratio of the external output, but it can also run full screen. Oh, I forgot to put, sorry. Let's run it again with Gallium to get the FPS. Nice when it's not going to start for sure. Getting there. It is there, okay. Okay. We're getting over 100 FPS, so fairly decent and definitely playable. So I think this gives us a rough idea of how this native context enables actually to run these games on a VM. I cannot run commercial games here, basically because this MacBook only has 8 gigabytes of RAM. But if you want to see more complex and commercial games about the running here, Asahilina did a live stream. He tested a number of them. You can download this. There are links on the slides when you want to check it out and actually confirm that you have quite a bunch of commercial games. Many of them quite expensive in CPU terms and GPU terms and work perfectly fine at 60 FPS. Yeah, you can run Crisis and yeah. So it's good. So I think that's all I had. Any questions?
So how about the Linux host? So can we run this cross-domain and also native context on the Linux host?
Running cross-domain on the Linux host. But
I mean, Asahi Linux is on Mac OS hardware, right?
yes,
Sorry. Yeah, I mean it's other normal like x86 machine or other hardware. Can we run that?
can you run that on x86 hardware? Yeah, in fact, they probably makes less sense because I mean here we are trying to cover two challenges. The first one is that these games are x86 games, so we need to emulate them because we are running on an ARM architecture. And the other problem is that also we needed a VM because we need to run a 4K kernel on top of a 16K kernel host. But if you wanted to have additional isolation on x86s, this should work perfectly fine. Yeah, the only requirement is that you need to have a device, a GPU driver that is supported by the DRM native context, which, as I said before, there are those three. Sorry, four. MSM, AMD GPU, Intel, and Asahi. Well, Asahi for x86 doesn't make much sense, but one of those three.
Okay. Another question is DRM I control interface will be sometimes changing, right, for different vendors. So we have to handle for different kernel versions, like for different interface. Okay.
Yeah, that's kind of one of the challenges of DRM native context over other contexts because, I mean, for Vulkan, you don't expect the Vulkan to change behind your feet because, I mean, if it changes, it's going to be an extension, so you can prepare for that. For OpenGL, it's the same story. For DRM native context, that means that you have to have the virtual, Mesa, and the kernel driver always in lockstep. So you need, every time you increase the UAPI, you need to coordinate all three updates. This is especially a challenge for the Asahi driver because it's not yet upstream. So that means that every time Asahi needs to update this kernel or Mesa or virtual render, it needs to update all the three at the same time. But yeah, that's definitely a challenge.
Will there be any capability check or some protocol to make sure we have the same correct binding? Or
Yes, during the context of the initialization of the context, you exchange data between the guest and the host. So one of the things it does is verify that the UAPI is aligned between the kernel, well, the different components, the guest kernel, the guest user space, the host kernel, the guest user, and the host virtual renderer. Yes, it's verified.
Thank you.
Welcome.
How stable is Asahi's API now? So you relies on this API now, right?
Well, instead, when you try to do a live demo, it works very well.
I mean, the interface stability. So you relies on DRM interface, so it will break if the upstreamed driver changes, right? So how
Yeah.
is it going to change again, or is it?
Yeah, right now there are no UAPIs guarantees for Asahi. So the thing is, until the GPU kernel driver has been upstream, the UAPI is not guaranteed to be stable, and it will change and it will break user space, which is why the reason why we need to update all three components at the same time. But when it eventually gets upstreamed, we expect it to be stable.
Okay. Right. Thank you.
Welcome. No more questions. So thank you all.